up your engines as we investigate real-time motorcycle tire dynamics with Flavio Farroni, co-founder and CEO of Megaride. Join us as we uncover the cutting-edge collaboration between a motoGP team and UniNa Megaride's vehicle dynamics team, aimed at developing a real-time thermal and interaction model for motorsport applications. Explore the intricacies of predicting tire temperature distribution and optimizing grip performance through innovative computational strategies.
Good morning, everybody. Thank you for the kind invitation from Megaride. It's a real pleasure to be here today to meet so many old and new friends in this room. I'm a researcher at University Federico II. I'm going to talk to you about real-time motorcycle thermal and interaction tire model applied startingly from motorsport application, but after that to many other fields regarding vehicle dynamics. We are, first of all, a research group at University Federico II. We developed in 2016 a first spin-off company which is called Megaride. We are very deeply focused on tires. We work on multi-physical tire models. We developed a modular simulation platform which can be easily embedded inside VA-grade and any other kind of simulation environments. And we used to have this approach, which is science applied to races. What we do, okay, the font has gone, but anyway, we work for bike and tire makers using the vehicle data, using the vehicle as a sort of moving lab, estimating road grip, road wear, and many interactions regarding tires. Thanks to this kind of data, we can perform safety logic and smart mobility algorithms, and we help the customers to save, of course, cost and time in development. We work a lot on driving simulators. We are starting also to explore something regarding the two-wheel simulators, mainly on gaming in this moment, but we are happy things are moving in this environment. And we work a lot with this kind of advanced driving experience, working on the vehicle and the tire, in particular digital twin and the virtual tire development. And we are really deeply involved in motorsport, with which we work on tire analysis to optimize the strategies and to identify usually the optimal temperature and wear ranges in which to optimize the tires. Some very quick highlights on the group. We were awarded as Innovators Under 35. I'm not anymore under 35, but our group is averagely 31 years old. We were awarded as the first project in Italy for tech transfer, and we currently have 14 PhD students in the vehicle dynamics group, and we're able to carry out more than 20 master theses and 35 bachelor theses every year on pioneering projects. And we have the support of our facility, which we call the Tire Lab at our university. The company Megaride was born in 2016. We were awarded as Tire Technology of the Year and Vehicle Dynamics Development Year of the Year by Tire Technology International and Vehicle Dynamics International. Our team is growing. We're about 45, and we became a sort of tech holding group because there was first of all Megaride. We now have four spin-off companies which converged inside Megaride holding group. And we work currently with half of the Formula One team, with 2 MotoGP, Moto2, and Superbike. So we are currently involved in motorcycle environment. It's not a mystery. This presentation will be on a project we had with one of the teams we worked with in MotoGP. We had an exclusivity with Ducati Corse several years ago, and we developed the things I'm going to introduce you today, which were evolved further in the last years. Why we are here today? Because I would like to talk to you about what we do with our vehicle dynamics group in two-wheeled vehicles field regarding multi-physical models concerning ride, comfort, handling, and tire road interaction phenomena, and mainly on the identification of the parameters. We don't develop just the models, but we develop the procedures to identify the parameters of these models, which is very important, mainly in motorsport, because usually the tire manufacturers don't like much that you cut their tires, so we need to find a way to get that kind of parameters. First step, we need to get the input for the models from the motorcycle in some way. We developed mainly for cars, but currently also for bikes, a procedure which we call a trick, which means tire road interaction, characterization, and knowledge, which means taking the data from the vehicle as a sort of moving lab. So we take specifically an outdoor testing routine. We acquire the longitudinal and lateral speed. Of course, we need some basic vehicle parameters of the bike and from the CAN bus or from any other kind of acquisition system, the longitudinal and lateral acceleration, the yaw rate, the steering angle, and the wheel's angular speed. And after that, we're able to process, sorry for the fonts, the X, Y, and Z tire road interaction forces, the side slip angle, and the slip ratios of the bike. In this step, we have the possibility in this way to get the data from the vehicle, to process them through this specific procedure, and to get the information which are the input for our thermal model. In particular, the model uses the tire tangential forces, vertical forces, slip angle, slip ratio, camber angle, and wind speed. These are the basics. How do we do that, and what's the target? We want a tire thermal model, first of all, because we want to have available the thermal info on the inner layer of the tire, which are not usually measurable. We want to advanced analysis and simulation concerning the relationship between grip and stiffness with temperature. We want to predict the tire temperature local distribution in the motorsport events we are going to prepare. And we, of course, want to develop the proper setup of the bike respect to thermal and wear working range optimization. How the model is structured, step 2. The model basically takes into account about 6 different layers, which is tread surface, tread core, tread base, the belt, the plies, the inner liner. We also have a model which takes into account the inner layer, inner air dynamics, and the sidewalls dynamics. Everything is conceived to be hard real time. Everything I'm talking to you works in real time. It's up to 16 different ribs in lateral direction, because working with MotoGP, we go up to 65 camber angles, so we need to take into account very locally how the things are working on the different ribs. So it's 8 different layers in radial direction and 16 in lateral direction. Which ones are the main heat generation and heat exchanges we take into account? About the heat generations, the tire usually hits for the tangential force in the adherence and sliding area, which we call friction power. And also the tire heats up because of the strain energy loss effects, which are due to the cyclic deformation for hysteretic losses. The heat exchanges we need to model inside the model are the forced convection of the tire surface layer with the outside air. We need to take into account about the thermal conduction between the tread and the road, and the natural or forced convection inside the inflation chamber. Of course, we need to take into account about the heat conduction between the different tire layers as a thermodynamic system. Inside the model, the formulation is the implementation of the 3-dimensional Fourier equation in a 3-dimensional domain in real time. So everything is analytic, everything is conceived and coded in C code in order to be very lightly real time. Let's move to the step 3. Once we develop the model, one of the main things is getting the parameters of the models. We split them in 2 families. There is the thermal parameters and the structural parameters. When we talk about thermal, we talk about the conductivity and the specific heat of all the different materials in each different layer of the tires. When we talk about structural, we need to take into account about the strain and energy loss I mentioned, and the measurement of the contact patch areas. First step, thermal parameters. Once again, we work a lot with motorsport. We needed to identify a way which were completely non-destructive. We cannot cut the tire, and the tire manufacturer does not like to see the tires that have been touched too much. So the idea was a laser beam that affects the tire from outside at different thermal powers. We re-implement that kind of setup inside our model. So it's static, so it means we need to cancel the convection with outside. We don't have cyclic deformation, so we cancel the strain energy loss. We don't have the turbulences in inflation area, chamber, and we don't have the sliding and adherence area. Of course, we need to add the laser beam which comes from outside. So we reproduce that kind of situation. We let run the same experimental environment, and we are able to identify which are the values of the thermal conductivity and of the specific heat of each different layer once the model has reached the stability. So it's completely non-destructive. Second characterization, at our lab we implemented this kind of bench which allows us to go up to 550 degrees in order, thanks to a TechScan bench, to identify the footprint shapes in terms of vertical load, camber angle, and inflation pressure, because one of the main difficulties in the thermal model for a bike, respect to the car, is that, of course, the footprint moves continuously from one side to the other side due to the camber angle. And so we have the distribution of the friction power and of the strain energy loss in areas which are completely different in any moment. one of the nice things we also do, once again, for confidential tires, we need also to know what's the thickness of the tread layer, and we do that thanks to ultrasonic probes, which allow us to identify where the cords are set in order to put the right numbers and right parameters inside the model. The part regarding the strain energy loss is also very interesting in the motorcycle model, because the strain energy loss for a motorcycle bike is part of two different phenomena. We call the macro cell, the cyclic deformation mainly conceiving the cords and the plies, so the carcass of the tires, which of course heats up for the deformation. But in particular for the motorcycle tires, we have a micro cell, which is due to the viscoelasticity of the tire, which interacts with the stones of the asphalt, of the tarmac. And this is a very impacting phenomenon for this kind of high-performance tires. So we are able to identify the macro cell thanks to some specific track sessions in which performing some specific maneuvers, we are able to identify which is the impact of the longitudinal and lateral maneuvers on the heating up of the tires. And about the micro cell, we developed this specific tool, which is called Vesevo. It's a portable DMA. It's a tool with which we're able to identify the viscoelasticity of the tires with completely non-destructive methodology. And it's also available here in these days because we will have a booth that you can try it because it's very also nice to use. Once we get this kind of information, we put inside the model the distribution of the strain energy loss. So, for example, we have a 2000 Newton, 37 degrees of camber angle with an inflation pressure of 1.8 bar. And so we know that the strain energy loss is distributed, in this case, of course, on the ribs, which are lying on the side of the camber angle, respect to this kind of vertical load and inflation pressure. Of course, this model can be completely customized. So we can work with the CFD in order to identify which is the impact. For example, if I need to simulate some, maneuver when I'm behind my competitor, the energy flux is completely different, so I need to take into account about this for the thermodynamic point of view. We also worked a lot on exhaust blown diffusers for cars, for example, which are also coming out also in motorcycles, about what happened in the inflation chamber in the turbulences, or we can also study, for example, the effects of the over-inflation, because, of course, the behavior of the footprint changes dramatically. This is how the model works. I don't know if this kind of video will start. Yeah, sorry for the aliasing of the areas because the model runs quite fast, but you can observe that for low values of the vertical load, we have a very small footprint. For high values of the vertical load, the footprint becomes, of course, bigger. And taking into account of the camber angle, which moves from 0 to minus 60, and now it moves up to plus 60, the footprint moves from one sidewall to the other sidewall. So the volume is considered as we have the tire, we cut it on the top and it becomes a rectangular area. And so the footprint moves inside this kind of control volumes. So once we run the model, we can observe some very nice and interesting things. So for example, we can validate the friction powers. So for example, if we have a tire which is or a motorcycle which is going straight, we have a central footprint. And so of course the friction power will be observed in the central ribs of the tires. If the footprint moves from one side to the other side, of course this kind of distribution moves from one side to the other side of the volume. The same can be done also for the strain energy loss. So once again, the distribution is quite different, but if we are turning and lying and cycling, deforming the tires, we have the distribution of strain energy loss from one side to the other side, which of course is summed up with the friction power. This is what the model does. As I told you, it's 16 ribs. Here I put just the half because otherwise it was a mess to notice these kind of things. But this is the whole telemetry for some different laps of a motorcycle on the different ribs of the tire. So, for example, this was a lap in which the tire was working a lot on the right side curves because we have the right side ribs, which are a higher temperature rather than the left side, for example. This is one of the most important things, because once I have this kind of model, I can get the information about the tread core temperature, so the temperature inside the tread layer, because this kind of temperature is the outside, which can be usually quite easily measured by infrared sensors. This one cannot be reached by any kind of instrument. Why is it important? I'm skipping this. I will be back there, but because it's interesting to show you this directly, sorry. Because if I put on the same diagram the lateral grip, for example, for the front tire or for the rear tire, respect to the measured surface temperature, I get this kind of correlation which does not tell much to us. If I put on the x-axis not anymore the surface temperature, but the tread core temperature, this kind of diagrams becomes this one, which is able to let me know exactly which is the thermal range in which the tire is working at the optimal temperature. So the highest correlation between grip and temperature is the correlation of the tread core layer with the temperature, of course, or the tread core temperature with grip and stiffness, of course. I'm moving back, sorry, because I skipped something. Of course, the model has been deeply validated. So in this case, you can see for 5 ribs, for example, what happened comparing the external measured temperature with the model temperature. The interesting thing, one again, is the inner liner temperature, experimental and simulated. As you can notice, on the stabilized area, the model performs very well. This is the result of some years ago. So these results came from the old MotoGP version of this model. We were not much able to get the transient dynamics inside the inner liner, but now these things have been deeply overcome thanks to the new air model we put inside the thermal model. What more? We can observe how, for example, the tire is heating up. So the lateral friction power, longitudinal friction power, the strain energy loss. It's very interesting, for example, that the lateral ribs, so this one and the other one, are highly affected by lateral friction power because they are the ones, of course, when the motorcycle is lying. On the central ribs, it's everything about longitudinal friction power because when I give throttle and brake, everything is longitudinal slip. And there's the contribution of the strain energy loss, which is the blue one, which is a little smaller than the other ones, but trust me, quite important. The same can be said about the cooling effects. They are mainly the inner liner convection and, of course, the outer air convection with the air outside. And the conductivity with road is very negligible, as you can observe. And finally, we can put everything together. So for these trips, we can observe everything in any moment. So, of course, it can be simulated on a simulator inside your desktop application for preparing the next event or for tire development. I already showed you this. Finally, we are moving toward multiphysics. So what's the next point? Once I get a very reliable thermal model, I can put this inside the Pacheca environment. Because as you well know, Professor Pacheca did a great job a few years ago, but his model just took into account about vertical load, side slip angle, slip ratio, and camber angle, not anything more. He was, of course, forgetting the temperature and also something related to the viscoelasticity and of the road roughness. We put these things inside our advanced Pacheca, we call it adheRIDE, and it's able now to take into account all these kind of things. So it's how, of course, it's the process. So we get the data from the vehicle, but it can be also from the trailer or from the flat track, of course, bench. We put everything inside the thermal model, and so we finally identify the adheRIDE model, which is able to take into account how the longitudinal, lateral, and grip curve change with temperature, and they change quite dramatically. Everything can be put also, of course, in co-simulation. It can work in VI bike real time, VI motorcycle, any kind of personal MATLAB model. And what's the secret? We just put functions inside of the macro coefficient of the Pacheca model. As you know, the Pacheca model has fixed coefficient. Those coefficients for us just became functions, which are function of tread temperature, road roughness, and of the compound viscoelasticity. The applications, of course, could be in vehicle setup optimization, motorcycle vehicle dynamics development, lap time prediction, because this kind of tool also works in real time in the VI max perf, for example, or any other kind of similar environment. And yeah, these are some references, some publication we did. I think the presentation will be shared with anyone, so they could be useful. Thank you. That's all.
Thank you, Flavio. So who is volunteering to do a short summary of his presentation? No, really good, very good work. And sorry. Thanks for this.
We don't have time.
We have 1 minute. One question. Microphone.
Thank you for your presenting. I'm a member of Hankook Tire, so I'm really interested in your presentation. And I have one question. Would you introduce briefly the function of the laser type, how it can work instead of the tire cutting?
Instead of the tire?
Instead of tire cutting function. I mean that you in your presentation, the laser, the document, you introduced the document function.
For the thermal conductivity evaluation,
yes.
Yeah, it's quite simple. We put the tire on the bench, we put the laser beam, we heat up that spot at different powers, 1, 2, and 3 watt, so it doesn't smoke. We identify the temperature during the heat up and also the cooling down phase once we shut off the laser. And we resimulate that kind of environment inside our model, changing millions of times the values of the conductivity and of the specific heat of the different layers. The model is able to replicate the empiric condition once the real value of the conductivity and specific heat have been reached by this kind of iterative identification process.